in the last class, we learned that if we consider the angular momentum in the z direction, Lz, then slightly thinner. If you consider angular momentum in the z direction, then the magnetic quantum number m can have only discrete values. It
Excuse me,
is
sir, your screen is not visible.
oh, I did not share the screen. Sorry. Visible now? Yeah. So if you consider the angular momentum in z direction, we had concluded in the last class that the magnetic quantum number m can have only discrete values. And so on and so forth. Okay. So this is the alpha value, sorry. That the alpha means the actual values of angular momentum that you can measure. M, the angular moment, the magnetic quantum number can be 0, plus minus 1, plus minus 2, and so on and so forth. We did it only for the z direction, and we did not do it for the x and y direction. And you can easily see that can be done because you already saw what will be the expressions for the Lx and Ly, and you can follow exactly the same procedure. But I would say that's pretty much unnecessary because in the space there is no specific distinction of the z direction. Any direction is practically equivalent in the sense that you can turn the Stern-Gerlach apparatus in the x direction, and there is no reason to expect there will be a different result. So the x direction, y direction, these are also angular momentum in the x and y direction. These are also discretized in the same way. That means you can only observe these values of angular momentum. So exactly the same way. So I'll just write Lx, Ly behave the same way without deriving it. That stands to reason. What about energy? Energy means rotational kinetic energy. We know that the rotational kinetic energy, will that be quantized? We know that that is L square by twice I, in the same vein as we were writing kinetic energy in the translational element as p square by twice m. In the same way, this is the angular momentum square by twice of the I. And this L square has then three components. So if I turn that into the operator, it will have three components: Lx operator square plus Ly operator square plus Lz operator, and the eigenvalues will be square. Eigenvalues of this operator are L plus 1, H plus. So these are the eigenvalues where L can have only discrete values in the same way. It is 0, 1, 2, 3, and all that. That means it doesn't take negative values. And the rotational kinetic energy. So here it is. I can better. I'll specify that as a rotational energy. It will be clearer then. It's then clearer. Okay. So since this is true, therefore we can write the Hamiltonian operating on psi for a free particle, it is L operator square pi twice I operating in psi is the E psi in the time independent Schrodinger equation form. And since L square have these as the eigenvalues, therefore the observable energy, the energy values, the eigenvalues of energy, the energy values that are observable will be it will have these values L plus 1 h cross square divided by twice I. So for each individual situation, you will have a different value of the I, and thus this will define what are the values of energy that you can actually observe. But this has great explanatory power. For example, consider a molecule, something like say the hydrogen chloride molecule. Okay, you can in your mind's eye you can picture it as say a bigger molecule, bigger atom, and a smaller atom connected by a line like this, sort of a dumbbell, lopsided dumbbell. The chlorine is here, the H is there, chlorine is there. So this is the hydrogen chloride molecule. And this thing will tumble through space. It will rotate and it will tumble through space. Now, if we ask what are the rotational kinetic energies that it can have, these are actually given by this. It can have discrete values of rotational kinetic energy, and one can transit from one value of kinetic energy to another, releasing a photon, or it can absorb a photon and go from one value of kinetic energy, rotational kinetic energy, to another. Thus, this picture will actually tell you how to interpret, for example, spectra of such a molecule. I'll give you a tutorial on that where you will actually have to work out or explain the specific absorption points, why these observation points are absorption points are observed. Okay, now let's continue. In classical mechanics, we have seen that angular momentum is conserved unless you apply it to it. So I'll clear it up. Let me clear it up. Okay. Now let's go to conservation of angular momentum. Actually, all conservation things are to be obtained from the generalized Ehrenfest theorem, which we have already seen. I'll write it once again. Of something, some operator. In this case, we'll replace that by LZ operator. We are trying to figure out whether LZ is constant or not. It is 1 by IH cross. It will be the commutator of LZ and the Hamiltonian. So this is from the Ehrenfest theorem. So from the and we also know that if it is a free particle without any V function, then the Hamiltonian operator is 1 by twice m. It is px square plus py square plus pz square. And what is our LZ operator that we know. It is easier to work out in the Cartesian coordinates, so I'll write it in Cartesian form, not in the polar form. It is x p y, something that we have seen in the last class, y px. So the commutator, if you want to work out of this commutator, the commutator will be L Z H will be this will be 1 by 2m. Then it will be this term x p y minus y px. This is our LZ, and then this px square plus py square plus pz square. This we have to work out. And we can see that these will have terms, this times this, minus this times this, and it will have terms like x, py, px, px square and all that. There will be a large number of terms. Let's make our life simpler without actually calculating. But most of these terms will actually cancel off because they commute with each other. All p's, px commutes with py square and things like that. Therefore, all these will commute and they will cancel off. What will not cancel off are the terms where x and there is py and y, px, and that kind of terms will not cancel off. And we have also seen that x and px square does not commute. We have seen earlier. So these are the terms that will remain. So effectively, what will remain, I'm just skipping steps. What will remain will be, it is 1 by twice m, and then it will be x comma px square. This does not commute, therefore that will remain, times py minus, sorry, square bracket. It is y py square px. These are the terms that will actually remain. The rest of the terms will cancel off. And we have earlier seen what these terms are. We have seen that, let's make a space here, x, px, this we have already worked out. If you turn your pages, you will find that in your note it is already there. This is twice I h cross px. And similarly, y py square will be twice I h cross py. So if you now substitute these here, then you get 1 by twice m. It will be, this will be px py. So I'll bring out, it will be 2I h cross. It is px py minus twice I h cross py px. And these two actually are the same because p in one direction commutes with p in another direction. This is equal to 0. So if this is 0, therefore the right hand side in this equation is 0, and therefore this operator does not change with time, and therefore angular momentum is constant. So we have concluded that angular momentum is constant. in z direction. All right. So this is something we have concluded. You might ask, you have used only a free particle without any v function. What if there is a v function? That question I have to answer. Let me just quickly answer that question. What if there is a v function? Now the v function could be anything, but of interest to us will be a v function that is spherically symmetric. For example, the hydrogen atom has that kind of a v function. So if say your Hamiltonian operator is 1 by twice m, the kinetic energy part will remain the same, px square plus py square plus pz square plus some vx. Now we consider this to be a radially symmetric v function. Then we know that Lz commutes with this whole quantity. So effectively the question boils down to whether Lz commutes with Vx. So Lz we know, this time we'll write Lz in terms of the polar coordinate minus I h cross del phi. So then we have Lz v. Now it is a function of the radial vector only. This thing operating on some function of r theta phi will be this we know, therefore we substitute it here, minus I h cross del phi. Then it operates on Vr f r theta phi. Now this is equal to, I'll first write is cross. Now this Vx actually the differentiation with respect to phi does not see Vr because it is only dependent on r, so I can bring it forward. It is Vr. And this one is, well, this is only the Vr because now we are writing all the operators have been written in their form. So Vr is nothing but a function of r that multiplies with f. So we can bring it forward. So it will be Vr times del phi of f r theta phi, and I can then bring this one forward and this one here. It is immediately clear that it is V r times L z. So therefore these two also commute, and if L and Vx commutes or Vr commutes, I'll rather put this one in terms of r. That is what we have considered. So we have considered in terms of r. So if these commute, obviously the whole Hamiltonian function commutes, and therefore the z component of angular momentum is constant even in a radially symmetric potential. And if the z component is constant, there's no reason to believe the other components will not be constant. So the others are also constant. So effectively we have proved that in quantum mechanical domain also, if there is a radially symmetric potential, the angular momenta are constant. Okay. Now let us work out the commutation relation. Now we'll use the generalized uncertainty principle which you will recall we had derived in this form for any two observed variables. These were greater than half then magnitude of base and the commutator of A and B. So that was the generalized uncertainty principle. The generalized uncertainty. And then now we are trying to figure out this, where the A operator is the angular momentum in x direction and B operator is the angular momentum in the y direction. So effectively we are trying to work out, we need to work out Lx, Ly. Okay. And in order to work this out, we will apply, first, it will be Lx Ly minus Ly Lx. We apply that on F. So effectively, we need to work out each of these quantities separately. So I'll just get some space and I'll first work out what is Lx Ly operating on some function F. We have not yet worked out Lx and Ly in terms of the polar coordinates, so we'll work this out in rectangular coordinates. So it is minus h per square. It is y del z minus z del y, and this is z del x minus x del z operating on F. And then you need to multiply this. And multiplication will be a bit longish, but I'll not work out the whole thing. The first term will be y del z, and it will be multiplying with this. So it is del z of z, which will be 1. So del x. Plus it will be this one of with this, so it will be del x del z and then del z, and this one will be z square del x del y and all that. So there will be a lot of terms. Basically there'll be terms involving second order partial derivatives. This one has first order. Partial derivatives. And then if you work the other one out, Ly Lx, then if you simply do this in the opposite order, you will find that then it will be minus h cross, square. Square, it will be x del y. There was a f, so f यहाँ पर आ जाएगा, f plus, and it will again be a set of terms that are in the second order partial derivatives. And it so happens, if you really work this out, I'm just going a little faster. If you work this out, you will find that these terms are the same. So when you subtract this from this, these terms will all cancel off, leaving behind only these terms. So what we ultimately get is that Lx Ly operating on F will be this minus this. It will be only minus h cos square will remain, and it is y del f del x minus x del f del y. And we know that this is nothing but uh, I can separate this out by saying that this is I h cross minus I h cross. Okay, then it remains the same. And then this term this is the not the same. There's a minus, so therefore I'll make this opposite. X del f del y minus y del f del x, and this is something we know. This is nothing but I h cross L z as an operator operating on f. So we can find that the operator Lx Ly, its commutator is nothing but I h cross Lz. Now, this is a result that we will need, so I'll just block it. This is an important result. It essentially means that Lx and Ly do not commute. And since there is nothing holy about the direction Lz, this is actually applicable to all the directions, and you can easily work out exactly in the same way. You can see that they are cyclically symmetric, and so this will work out in all the directions. Okay. So I'll just delete this part, the part that I've used as, can delete the whole thing. So we have found a symmetric relation Lx Lx Ly is I h cross Lz. Similarly, Ly Lz equal to I h cross Lx, and Lz, the cyclic symmetry essentially, is equal to I h cross Ly. Now there is a great deal of implication of this. For example, we earlier learned that the angular momenta can have these values. So angular momenta actually in each direction. So in each direction, will be 0 plus minus h cross plus minus twice h cross, and so on and so forth. So the angular momentum in the z direction could be plus h cross. Angular momentum in the y direction could be twice h cross. Angular momentum in the z direction could be minus twice h cross. So is it possible? So let me write. Angular momentum in the x direction is say h cross. Angular momentum in the y direction is say minus twice h cross. Angular momentum in z direction is say plus twice h cross. So each of these are possible, right? Because of this. Is this possible? This whole combination? No, that is not possible because of the commutation relation. Since Lx and Ly do not commute, therefore the moment Lx is specified, Ly cannot be specified, it cannot have a definite value. Similarly, when Lx is specified, Lz can also not have a definite value because Lx and Lz do not commute. So this is not right. and this is not right. Cannot have these values. Even though these possibilities indicate that these values may be possible, but independently. All of these cannot have definite values at the same time. This is somewhat difficult to grasp. I understand that because when I taught in the earlier years, it took quite some time for students to grasp this particular issue. But fortunately, this was probably taught once in the last semester, and I'm also telling you again. And therefore, you will slowly come to terms with this fact. Essentially, it is like the usual uncertainty principle. If x is known, p is unknown. If p is known, x is unknown. In the similar way, if the angular moment in the x direction is known, the angular moment in y and z direction are not only unknown, they cannot have definite values. It's not that we are unable to measure them correctly. It is basically they do not have definite values. Okay. And the uncertainty principle will demand, let me write them here, will demand that the uncertainty in x and the uncertainty in y should be greater than the okay, and similarly the uncertainty in y, the uncertainty in z direction will be greater than. These follow from the generalized uncertainty principle. It will be yzx. And the uncertainty in z and uncertainty in x will be greater than x cross by 2. It is Ly. So these three directions of angular momentum will have elemental uncertainty. Now the question is, what about L square? We have seen that the energy is related to L square. Do these individually commute with L square? So it will be a longish calculation. Again, I'll avoid the longish calculations because we are committed to go a little faster. So I'll only state the result that L square does commute with these quantities. Lx, this is and it is same as L square Ly and same as L square in the z direction and equal to c. So they do commute. Okay, so L square commutes with all these individual angular momenta. So the total angular momentum square is actually commuting with each of these, and therefore total angular momentum can have a definite value. So if this is given, that means a particular value is given, still the total angular momentum can have a definite value, and the energy, rotational kinetic energy, is dependent on L square, and therefore the kinetic energy can also have a definite value. So, so let me write it because it's important. T can have a definite value. So we concluded that if one value is defined, then the other two are not defined, but L square is defined and the energy is also defined. Okay. All right. Now let me delete this and continue, because now we do not have the space that I was earlier using. Then my pen becomes a bit messed up. One important point we need to consider is that the z component of angular momentum, the z component or any component for that matter, angular momentum cannot exceed the total angular momentum. Obviously, this is obvious. So this implies that what we have taken as the two quantum numbers, m, the magnetic quantum number, and L, these two cannot be completely independent of each other. This immediately means that the angular momentum in the z direction was m h cross. It could be positive or negative. That magnitude should be smaller than it was L plus 1 h cross square. It was the magnitude of L square, and therefore it would have to be square root. So if I took the square root, I can delete the square here. That will be okay. So it has to be smaller than this. So you can see that if so effectively it means that since m and L are integers, since integers, it effectively means that magnitude of m should be less than L. So if L is given, then so for the m can take values 0, plus minus 1, plus minus 2, all the way to plus minus L, not all the way to infinity. It can only go up to plus minus L. That is an important, and that's probably what you have used in your work on the hydrogen atom. So this is what is actually used. So it can take 2L plus 1 different values, including 0. So this is actually 2L plus 1 different values. Okay. Let us define Lx plus ILy is equal to L plus. So this is defined. And Lx minus ILy, I'll show that these are the raising and lowering operators, but I'll let me just draw a line here so that you know. Okay, so these are the two definitions. We have defined the L plus and L minus. Well, what do you do with it? You notice that you have already seen that Lz comma Lx is equal to IH cross Ly. All these are operators. And Ly, Lz is equal to IH cross Lx. This is something that you have learned earlier. So this equation means that Lz Lx minus Lx Lz is equal to IH cross Ly. All these operators. And this one means Ly Lz minus Lz Ly is equal to IH cross Lx. Let's call it 1 and let us call it 2. Now, now we need to do something with this. So let us take minus of 1 and multiply do with I, then what happens is this one will be minus Lz Lx plus Lx Lz is equal to minus I h cross Ly, and this one will become I Ly Lz I L minus I L Z L Y is equal to I will be plus, will be minus H cross Lx. So all these are operators, so I'm not bothering to put hats on them. So if you now subtract, you will get Lz will come common. It is L while Lx plus I Ly, it will be Lz minus Lz Lx plus I Ly, that will be equal to minus H cross Lx plus I Ly. So all these are the same. So that immediately comes to the conclusion that L plus as an operator, its commutator with Lz, uh, is minus H cross L plus. In a similar way, without spending much time on that, you do similar calculation. Similarly, you can show that uh, L minus and Lz, they their commutator gives H cross L minus. Okay. So now, after having obtained these results, we you see, you have already learned when I was doing that the eigenvalues of the Lz operator is mh cross. So where m goes from minus values to plus values, integer values. This is what we obtained by actually demanding that the function should come back to itself as you go 360 degrees. So this is what we had already obtained. And so for each value of m, there will be an eigenvalue and there will be an eigenvector. Let's call that eigenvector as m ket. And let us operate this on the m ket. So you have L plus and Lz, its commutator operating on the ket m, it will be minus H cross L plus ket m. This equation, we are operating both sides on the ket m. Okay. This gives I'll break it up, L plus Lz ket m minus L plus Lz L plus ket m is equal to minus H cross L plus ket m. Well, now let me bring this one to this side and write it as Lz operating on m gives mh cross as the eigenvalue. So we know that. So it is L plus mh cross we get M. And we bring this one here plus H cross L plus get M. This one to the left hand side. Then this one will be in the right hand side. LZ L plus get M. Okay. Now here you can see that this is a number, so this can be brought to the front. So it is basically M plus 1 H cross L plus M is equal to LZ L plus M. This means that the LZ is operating on this to give this times the same thing, which means that L plus M is an eigenvector of LZ with eigenvalue M plus 1 H cross. Okay. So that leads to the conclusion that L plus M is an eigenvector, also an eigenvector of LZ with eigenvalue M plus 1. It started with M H cross. Now it becomes M plus 1 H cross. So it just raises one level. So you see L plus operating on M raises it one level. You get a eigenvector with eigenvalue that is one level higher than that. So that is why it is called a raising operator. And in the similar way, you can show that L minus lowers it by one level, M minus it will happen. So you have a situation where that is a lowering operator. So that comes to the conclusion, the L plus is a raising operator. L plus is a raising operator. And L minus is a lowering operator. Now, if I start with a state, because you know that M goes from 0, minus 1, minus 2, minus 3 and all that, and goes up plus 1, plus 2, plus 3 and all that. So all those values are there. But then will there be any limit? Can it go to infinity, going up and up? Because if you keep on applying the L plus, will it go up and up? That it cannot, because the total angular momentum, the angular momentum along the z direction cannot exceed the total angular momentum, which is a finite number. And therefore, we know that there has to be a limit. So you can easily see then that we have a situation where I can draw a vertical line, and then there will be a level which is 0, level which is 1, level which is 2. They need not be equally spaced. We do not know whether they're equally spaced or not. Minus 1, minus 2, minus 3, and so on and so forth. But you know that it ends somewhere. So it ends means, if you recall what you did in case of the harmonic oscillator, where you use the lowering operator to go from a higher level to a lower level, but if you apply the lowering operator to the ground level, then you get 0. It is nothing. So here also similar things should happen. So let us consider that there is some level up here, which is the maximum, highest level. So this is the highest level. So let us call it M is equal to some number L. And we know that the total angular momentum is Lx square plus Ly square plus Lz square. Okay. I'll do a little bit of jugglery with this you just keep on noticing what I'm doing. I will keep the LZ square intact, but then I will replace this by Lx plus ILy and Lx minus ILy so that it becomes something like this. So I will plus Lx plus ILy, Lx minus ILy. If you are not careful, you will think that this is equal to this, but it's not, because Lx does not commute with Ly, and therefore the cross terms will remain, right? So Lx square is fine, Ly square is fine, but Li minus I Lx Ly plus I Ly Lx will be there, and therefore it will be, then you have to subtract that, minus I, it will be Lx, comma Ly. Without that, there will be a mismatch. And we know what these are. So we can write Lz square plus L minus, I'll writing downstairs or upstairs, probably downstairs. Anyway, L plus, this is something that we know, and this will be minus I. This is something that we know. It is minus I times I H cross Lz. Okay. So we can write this, the whole thing, as Lz square plus II plus, it is H cross Lz plus L minus L plus. Now I apply that on this level. So apply that on the highest level. So you have L, this is something that I did not do at that time, so I need to finish that up. That is applied on the L gate. It will be all these applied on the L gate. It is Lz square applied on the L gate plus H cross Lz applied on the gate L plus L minus L plus applied on the L gate. Now, L plus applied on the L gate, this is the largest level, highest level. Now, if you want to raise it further, you get nothing, 0. So this will lead to 0. You are left with only this. And this is Lz applied on L. You know that it leads to H cross L. So it is twice applied. So H cross square L square. That is the eigenvalue then. And then this is plus H cross. Once applied, it will be H cross L applied on L. So this is nothing but H cross square L plus 1, this get L. So you see the eigenvalue of L square is L plus 1 H cross square. Okay, so you might argue that this is only applied to the highest level. What about the other levels? So what we do is apply L square, but the L minus applied on the L. We know that this will get it to the one level down. So this will become again the same thing. It is L minus is something that commutes with L square. So we can write it L minus L operator square. Then it is the get L, and this result we know. So L minus, and it is L, sorry, I don't need to put this bracket. L plus 1 H cross square and L. So you can easily see that H cross, we can bring it forward, L plus 1 H cross square, then L minus, because this is a number, L minus operating on L. So it is clear that L minus operating on L is an eigenvector of L square with the same eigenvalue. Do you notice then that all the levels will have the same energy? Okay, next I will better deal with the issue of what you learned earlier, that if there are operators that commute with each other, while we're dealing with matrices, we did a theorem that says that if there are operators or matrices that commute with each other, then they will have simultaneous eigenvectors. So if there are operators that commute with each other, they will have simultaneous eigenfunctions. Okay, so if we try to work that out, then let us consider a spherically symmetric system or a for a spherically symmetric system, we know that Lx, Ly, Lz are conserved. Hmm? We know that uh, we know that Lx, Ly, Lz uh, all commute with the Hamiltonian operator that we have seen for the spherical symmetric system. Hmm? And and L x square, Ly square, Lz square also commute with Hamiltonian function. How, if you want to have a proof, it's clear, I can clearly show that it is Lz square and then the Hamiltonian. This can be written as Lz Hamiltonian. And then since these two commute, I can bring Hamiltonian forward. And then these two commute, therefore I can bring further forward. So this is Hamiltonian Lz square. So the Lz and Hamiltonian commutes, and in the similar way, Lx, Ly square also will commute. Okay. So what we have decided is that, what we have found is that the Lx, Ly, Lz all commute with H. Lx square, Ly square, Lz square all commute with H. The full L also commutes with H. So L square is Lx square plus Ly square plus Lz square. Since each of these commute with H, therefore the whole thing will commute with H. So also so it implies that all the operators that commute with each other will have a simultaneous eigenfunctions. Simultaneous eigenfunctions. So Lx, H, and L square will have simultaneous eigenfunction. But Lx and Ly do not commute with each other, so they will not have simultaneous eigenfunction. But each of these can have simultaneous eigenfunction. So let me write it. I'll do it in z direction because Stern-Gerlach apparatus is considered normal in the z direction. L square and H. They must have a set of simultaneous eigenfunctions. Now, in the states represented by the simultaneous eigenfunction, all of these have definite values. So that means the z component of angular momentum, the L square and the h, they all will have definite values, where in that particular state represented by the simultaneous eigenfunction. So the theorem that we proved earlier essentially means that all these commuting variables, commuting operators, will have simultaneous eigenfunctions, and these simultaneous eigenfunctions can then be made into basis, and in that basis all these operators will be diagonalized, and then we can easily find out all these diagonal terms will be the eigenvalues, and they can be observed. They can all have distinctly observable values. Whatever just I said, it represents that all these will have distinctly identifiable values. Good. So we have more or less done what I wanted to do in angular momentum. And you can see that whatever we set out to prove that angular momentum will be quantized, we have been able to prove that. So all is well. Or in the language of Three Idiots, all is well. But is all well? Let's just quickly check that out. Is really what we set out to explain has been explained. Quickly check that. Okay. We have seen that for each L, M can have zero, plus minus 1, plus minus 2, all that. Suppose L is 1, then it can be 0, minus 1, plus 1, 3. L is 2, it can be 0, plus minus 1, plus minus 2, 5. Note that always M, the number of M's, is odd. And therefore, M is odd means the angular momentum in the z direction can have odd number values, which means our prediction from this theory will be that if you do a Stern-Gerlach experiment in the z direction with magnetic field oriented in the z direction, you will have 3 spots. But I have already showed that the experiment showed that there are only 2 spots, which essentially means all that we have done actually does not explain why there are 2 spots. Even though that shows that it has to be quantized, but the theory that we have developed so far does not explain the experiment. It does not say, it predicts that there has to be odd number of spots to be more accurate, but we have found that there's even number of spots. Therefore, what we have talked about in terms of orbital angular momentum, that does not explain the observation, and we need a completely different theory to explain it. And that's what we'll do from the next class.